Hello and welcome to Controllers Tech. In the previous videos, we covered semaphores and mutexes, two ways to synchronize tasks in FreeRTOS. Semaphores are great for signaling between tasks, and mutexes are the right choice when you need to protect a shared resource. But both of them have one limitation: they can only represent a single condition. Either the semaphore is available, or it is not. So what if you have multiple events happening at the same time, and you want a task to react to any one of them, or wait for all of them before doing something? That is where event flags come in. Let me explain how event flags actually work. Internally, an event group is just a 32-bit value. Each bit in that value represents a different event. When an event occurs, the corresponding bit is set to 1. When it is cleared, it goes back to 0. Now, FreeRTOS reserves the top 8 bits for internal use, so you have 24 bits available for your own events. That means you can track up to 24 different events using a single event group. You define your flags like this, each flag setting 1 bit in the event group. Each flag is just a unique bit position. When sensor 1 fires, bit 0 gets set. When sensor 2 fires, bit 1 gets set. And so on. Now here is where it gets interesting. When a task waits for event flags, it has two options. It can wait for any of the specified flags, meaning it unblocks as soon as at least one flag is set. Or it can wait for all of the specified flags, meaning it only unblocks when every single flag it is waiting for has been set. This is something a semaphore simply cannot do. With a semaphore, you can only wait for one thing at a time. With event flags, you have full control over when your task wakes up. You can tell it to sleep until every single expected event has occurred, or you can tell it to react the moment the first event comes in. That flexibility is what makes event flags so powerful in real embedded applications. In this video, we will cover 3 things. First, we will see how to use event flags to wait for all 3 sensor events before processing. Then, we will switch to waiting for any single event, and see how to identify which event actually triggered the task. Finally, we will look at a practical example where a button press and a UART receive both trigger their respective tasks directly from an interrupt service routine. Let's open the Cube IDE. Here I have the project from the previous part, which is part 5. The first thing we will do is rename this project to part 6. Make sure you check the Update References box while renaming, so the name gets changed at all relevant locations. Alright, the renaming is done. Now delete the debug configuration file and also rename the IOC file to part 6. Next, open STM32 Cube MX and load the part 6 project into it. It is essentially the part 5 project, just the name has been changed to part 6. Now open Middleware, FreeRTOS, and go to the Tasks and Queues tab. The 4 tasks from the previous project are still here, so we are going to delete all of them and create 4 new tasks for this tutorial. Task 1, Task 2, and Task 3 will be used to set the event flags, while Task 4 will read those flags and print the data on the serial console accordingly. All 4 tasks will have normal priority and a stack size of 512 words. Now go to the Mutexes tab and delete the mutexes that were created in the previous project, as we do not need them anymore. Next, open the Event Flags tab. Here we will add one event group. Leave the name as MyEvent01. Also keep the allocation dynamic, so the event group will take its memory from the FreeRTOS heap. If we check the heap usage, we still have enough heap available, so we are good to go. That is all we need to configure here. Click Generate Code to generate the project. Alright, the project has been generated, so let's go back to QIDE. Here, inside the main function, you can see our 4 tasks have been created, and below that the event group is also created using the function osEventFlagsNew. Now scroll down to the tasks. Let me first delete the leftover code from the previous project. Now, each task will set 1 bit of the event flag, so let's define those bits first. Task 1 will set bit 0, Task 2 will set bit 1, and Task 3 will set bit 2 of the event flag. Now inside Task 1, we will first print a log message on the serial console, and then call osEventFlagsSet to set bit 0 of the event flag. Note that if you want to set multiple bits at the same time, you can OR them together. For example, ORing task 1 bit and task 2 bit will set both bit 0 and bit 1 in a single call. But for now, we are only setting bit 0, which indicates that the event was generated by task 1. Let's also add a delay at the end so the other tasks get a chance to run. Similarly, task 2 will set bit 1 and task 3 will set bit 2 of the event flag, each with their own separate delays. Now, task 4 will read the event flags. We will first print a log message indicating that the control is inside task 4, and then call osEventFlagsWait to wait for the events. This function takes 4 parameters. The first is the event group handle. The second is the set of flags we want to wait for. Here we are providing all 3 flags. The third parameter decides how the function waits for these flags. If you use osFlagsWait any, the task will unblock as soon as any one of the 3 events is generated. If you use osFlagsWait all, the task will wait until all 3 events have been generated. So even if task 1 sets its flag, the function will continue waiting for task 2 and task 3 as well. By default, the flags are automatically cleared once they are read by this function. However, if you do not want them cleared automatically, you can OR in the osFlagsNoClear option. The fourth parameter is the timeout. If you set it to 0 and the event has not been generated yet, the function will immediately return an error. If you set it to osWaitForever, the task will remain blocked until all the required events are generated. We are going to use osWaitForever, which is the right approach here. After the events have been read, we will print a success message on the console. Alright, let's test this much first. Build the project and flash it to the board. Now open the serial console to view the logs. Here you can see that the processing task was waiting for the events first. Then task 1 generated its event, task 2 did the same, and task 3 also generated its event. Once all 3 events were generated, the processing task printed a success message indicating it has received all the events. The same process repeats again. Task 1 generates its event, task 2 follows, task 3 does the same, and once all 3 are set, the processing task prints the success message again. This confirms that the event flags are being cleared and reset properly after each cycle. So waiting for all events works just fine. The task waits until all 3 events are generated before proceeding. This can be useful in situations where you have different sensors reading current, voltage, and temperature separately, and you want to combine their data to generate a single output. For example, imagine a power monitoring system, where you need readings from all 3 sensors, before you can calculate the total power consumption. If you processed each sensor reading individually, your output would be incomplete. But with event flags, you can ensure that your processing task only runs once all 3 sensors have reported their data, giving you a complete and accurate result every time. Now, it is worth mentioning that waiting for all events does not mean you have to wait for every single event in the group. You can choose to wait for only task 1 and task 2 events, and completely ignore task 3 if you do not care about it. Now that we understand how waiting for all events works, let's see how we can use the same tasks but wait for any one of those events instead. So instead of using osFlagsWait all, we will use osFlagsWait any. In that case, the function will succeed as soon as any one of the 3 events is generated. I also want to print which particular event was triggered, so we need to make a small change here. The osEventFlagsWait function returns the flag value containing the event data. We will store that return value in a 32-bit variable, and then check which particular bit is set in that variable. Based on that, we will print a log message telling us which task generated the event. Now with the current logic, task 1 would keep firing every second and dominate the output, so let me give each task a separate delay. Task 1 will run every 3 seconds, task 2 will run every 5 seconds, and task 3 will run every 7 seconds. Alright, let's flash this updated project to the board and see the output on the console. You can see that task 1 generated the event first, and the processing task read it correctly. Then when task 2 generated its event, the processing task printed that as well. And when task 3 generated its event, it printed that too. So the processing task is now succeeding whenever any one of the 3 tasks generates an event. Notice how the processing task does not wait for the other 2 tasks anymore. As soon as one event comes in, it handles it immediately and then goes back to waiting for the next one. This is a much more responsive behavior compared to waiting for all events, and it is very useful in situations where each event needs to be handled independently as soon as it occurs. Now let's take a practical scenario where we can use these event flags. We are going to use a button to blink an LED, and add another task to print the data received over UART. The idea is simple: when the button is pressed, an interrupt will be triggered, which will set an event flag. The button task will be waiting on that flag, and as soon as it is set, it will toggle the LED. Similarly, when data is received over UART, another interrupt will fire, set a different event flag, and the UART task will wake up, read the data, and print it on the serial console. This way, both events are handled independently using a single event group. Let's go back to CubeMX and make some changes. First, in the Tasks and Queues tab, we will create a button task with a low stack size. Since it will not print anything, it will simply turn the LED on or off. We will also create a UART task with a stack size of 512 words, because it will use printf to send the received data to the serial console. Now let's configure the hardware. I am going to use pin PA3 to connect the button. The button will be connected between this pin and ground. So set this pin as an external interrupt, so that whenever the button is pressed, an interrupt will be triggered. By default this pin will be pulled high using the internal pull-up, and when the button is pressed it will be pulled down to ground. Make sure you also enable the interrupt for the XD3 line. Now let's look at the UART settings. The low power UART 1 is already enabled for logging. Here we are simply enabling its interrupt so we can also receive data from the computer in the interrupt mode. That is all the changes we need to make. Click Generate Code to generate the updated project. Alright, the new tasks have been created here. Let's go to the top of the main file. Here we are going to define 2 more event bits. One is the button pressed bit, which will set bit 3 of the event flag, and the other is the UART received bit, which will set bit 4 of the event flag. We will also define a buffer array here to store the data received from the UART. Now let's set up the interrupt callbacks. When the button is pressed, pin PA3 will go low, an interrupt will trigger, and the GPIOXD callback will be called. Inside this callback, we will simply call osEventFlagsSet to set the button pressed flag. Similarly, when data is received on UART 1, another interrupt will trigger and the UART complete callback will be called. Inside this callback, we will set the UART received bit of the event flag. Now inside the main function, before the FreeRTOS scheduler starts, we will call HAL UART receive interrupt to receive 5 bytes in interrupt mode. One important thing to note here is that the HAL library automatically disables the UART-receive interrupt after a single callback. So if you want to keep receiving data continuously, you must call receive interrupt again at the end of every RX complete callback. If you forget to do this, the interrupt will fire only once and then stop working. Now let's scroll down to the tasks. Inside the button task, we will call osEventFlagsWait to wait for the button pressed event generated by the XD callback. Since we are only waiting for one flag here, it does not matter whether you use osFlagsWait all, or osFlagsWait any, both will behave the same way. The task will remain blocked until the button is pressed and the flag is set, and after that it will simply toggle pin PB7 where the LED is connected. We will also add a small delay here to prevent button debouncing. Similarly, inside the UART task, we will wait for the UART received event, and once that flag is set, we will print the received data on the serial console. That is all the changes we need to make. Let's build and flash the project to the board. Let's test the button first. You can see that every time I press the button, the LED toggles. That means the button press is successfully generating the interrupt, which sets the button pressed flag, and the task is reacting to that event and toggling the LED. Now let's test the UART event. I am going to send 5 bytes of data to the STM32 from the computer. And you can see the data has been printed on the serial console. So when the 5 bytes are received, the UART interrupt fires, the UART receive flag is set, and the corresponding task wakes up and prints the data. So in this video we saw how to use event flags as a notification mechanism between tasks, and between interrupts and tasks. We covered both methods, waiting for all events and waiting for any one of them. We also saw a practical example of how event flags help keep the interrupt service routine as short as possible, by simply setting a flag inside the interrupt service routine, and letting the actual processing happen inside the task. I hope you now have a clear understanding of how event flags work, and how they can be used as a flexible signaling mechanism in FreeRTOS. That is all for this video. You can download the code from the article linked in the description. Leave a comment if you have any doubts. Keep watching, and have a nice day ahead.